So, now we shall start a new topic that is called inner product spaces, and this is also very important concept in linear algebra. So, recall that the vector spaces are usually algebraic extension of Euclidean spaces. In other words, that algebraic properties of the Euclidean spaces have been generalized and got that vector spaces. So, the next we shall generalized the distance and length of vectors concept of Euclidean spaces. So, we shall impose some more structures to vector spaces and get a new space that is called inner product space. In case of Euclidean spaces, vectors have length and we find distance between any two vectors. So, that concept we shall generalize to a vector space. Remember that in case of Euclidean spaces, we have those scalar product, and in terms of scalar product, we find that length of a vector and distance between any two vectors. So, something similar to that scalar product we shall define in a vector space, arbitrary vector space, and that is called inner product. So, that we define an inner product in a vector space. So, let V be a vector space over a field F. Of course, here we take this field F as set of real numbers or real field or complex field. An inner product in that is in V, an inner product in V is a mapping we denote by this from this V cross V to this field F, such that for vectors u, v, w in the vector space and scalar alpha in the field F, first condition is that u plus v comma w, or this inner product of u plus v comma w is equal to u w plus v w. Second axiom is that alpha u v, this is equal to alpha times u v. Third axiom is inner product of u v is equal to, if we change the order of the vectors, inner product of v u, its complex conjugate. So, here this the bar denotes complex conjugate. So, fourth axiom is for any vector u in V, u inner product of u with itself that is greater than or equal to 0 for all u belongs to this vector space. Equality holds if and only if u is equal to the 0 vector. So, any vector space together with a mapping this inner product, that is called an inner product, and which satisfy these 4 axioms will be called an inner product, and the vector space together with an inner product is called an inner product space. So, the vector space V together with this inner product is called an inner product space, So, here we must notice one thing, that the 4th axiom, that inner product of u with itself, this has to be a real number, otherwise we cannot say that this comparison that greater than or equal to 0. So, this actually follows this from this 3rd axiom. Let us write this as a remark. So, we have this remark. First one is that from 3rd axiom we get u inner product of u with itself is real, and therefore axiom 4 makes sense. This makes sense. Second remark is that if the field F is the real field, then axiom third will be inner product of u v is equal to inner product of v u, or in other words it is symmetric. Then third remark, in third remark we have, for F be the complex field, if we do not take u v is equal to the conjugate of v u, then we will get some inconsistency. We will have inconsistency, that is IU that is greater than or equal to 0 from axiom 4, and this is equal to I square u and this is equal to minus 1 u. So, this is less than or equal to, so this 0, less than or equal to 0. So, we have this inconsistency. So, fourth remark is that inner product of u with alpha v, that scalar is multiplied with the second component, then we get from axiom 3 alpha b u its complex conjugate, and this is equal to alpha bar V u, its complex conjugate. So, alpha bar u v. That means, if we multiply a scalar with second component, then when it comes out, we get its complex conjugate of the scalar times u v. So, let us see some example of inner product spaces. So, first one is this. This is very natural one that we take. Let V be the vector space Rn, F be the field set of all real numbers. So, for x is consisting of x1, x2 to xn and vector y with components y1, y2 to yn. In Rn, we define inner product of x and y as summation xi yi I from 1 to n. In fact, this is the scalar product of two vectors in Rn. So, one can check that this mapping will be an inner product and this space Rn together with this usual scalar product is an inner product space. So, one checks that this Rn together with this inner product is an inner product space, an inner product space. So, similarly, we will have an inner product in set of complex set of complex the vector space C to the power n. So, the second example is V be the C n, F is the field C for x vector x with components x1, x2 to xn and y with components y1, y2 to yn. In Cn, define this mapping as summation xi yi bar, this is complex conjugate again, I from 1 to n. So, again one checks that this mapping is an inner product in Cn. So, therefore, this Cn is also an inner product space. Third example is here we consider V be the space of all complex valued functions on this interval, closed interval a b. We define a mapping F. So, this mapping from V cross V to set of complex numbers as F g is equal to this integral A to B F T G T bar, this is the complex conjugate of G T dt. Again one can check that, this mapping is an inner product in V. So, let us see another example, that here we consider V B the set of all n by n matrices with complex entries. Set of all n by n matrices with complex entries, that is the set of all n by n complex matrices. So, here we define for A B belongs to V with entries of A B A I J, entries of B are B I J, define this mapping A B is equal to summation A I B I its complex conjugate I from 1 to n. Here one checks that this mapping, one can verify that this mapping satisfies all the axioms of an inner product except that inner product of U with itself is equal to 0, implies that U equal to 0. That is, inner product of A with itself is equal to sum of this A I, this mod square I from 1 to n, this is equal to 0. This implies that the diagonal entries A I are 0 for all I, but it does not imply that A I j is equal to 0 for I not equal to j. Therefore, this mapping we have defined is not an inner product on this set of all n by n complex matrices. So, next we shall see some important properties of this inner products. Before that, we have another terminology, that let this V be an inner product space. here we write simply V. Whenever we say that this V is an inner product space, we understand that there is an inner product defined on V. So, for any vector u in V, the positive square root of this inner product of u with itself is called the norm of u, and we denote this by this norm of u, that is, this norm of u is the positive square root of u. For any two vectors, u v in this inner product space V, the distance between them is d u v is given by norm of u minus v. Then here we shall see some properties of this norm. We shall write this as a result, the theorem. So, let V be an inner product space, and u belongs to V, u be a vector in V and alpha be a scalar, then the following hold. First result is that norm of minus u is same as norm of u. Second result is that norm of u is greater than or equal to 0, equality if and only if u is 0. Of course, this follows from fourth axiom of an inner product. Then this third result we get here is this: norm of alpha u is equal to absolute value of alpha times norm of u. So, this first and second are trivial. First and second are trivial. For third result, we have norm of alpha u square is equal to, from the definition of norm, inner product of alpha u with itself, and this will be alpha bar inner product of u with itself, and that is equal to absolute value of square of absolute value of alpha times u, or from here we get this norm of alpha u is equal to that absolute value of alpha, and this of course this is equal to this mod alpha square and norm u square. So, that is why you get here, we get here that norm of alpha u is equal to absolute value of alpha times norm of u. Next, we shall discuss an important inequality in an inner product space, that is known as this Cauchy Schwarz inequality. Cauchy Schwarz inequality. This is very important. So, here it states that we consider again that V be an inner product space, for any two vectors, u v in this inner product space V, that absolute value of inner product of u v that is less than or equal to norm of u times norm of v. Further, equality holds if and only if u and v are linearly dependent. So, since this is an important result, we shall see a proof of this theorem. Notice that if V is the 0 vector, then the theorem holds trivially, So, let us take V be not the 0 vector, V be a non-zero vector. Now, for any real number t, we have the following. We consider the norm of u minus t times inner product of u v times v, this square of this norm, and from the definition of norm we get this inner product of u minus t times norm of u v times v with itself u minus t u v v. On simplifying, that we simplify using the axioms of an inner product space and get that norm u square minus 2t inner product of u v bar plus t square times inner product of UV, inner product of UV its conjugate, and inner product of V with itself, or this is equal to norm U square minus 2t absolute value of norm of UV square. This is from the property of complex numbers t square, that absolute value square of absolute value of this inner product UV square of norm of V. So, this is true for every real value t. So, here we consider a particular value of t, that we can take any real value for t. So, in particular let us take t be one open norm of square of norm V, and we get this norm of u minus t u v inner product of u v times v, this square is equal to, on simplifying we get norm of this u whole square minus inner product of u v its absolute value and square of this divided by square of norm v. So, notice that this left hand side is, this is greater than or equal to 0 from the definition of this norm. So, we get this, so we get that this norm of u, this square minus this absolute value of v u, this square divided by square of norm v, this is greater than or equal to 0, or this inner product of u v its absolute value whole square, this is less than or equal to norm u square times the square of norm v. Then taking positive square root on both sides, we get the inequality in the theorem. So, then next for the second part, that equality part. So, for the equality part, first let u and v be linearly dependent, that is u is equal to alpha times v for scalar alpha. So, the LHS is, LHS will be absolute value of inner product of alpha b v, this is equal to absolute value of alpha inner product of v with itself. So, this is equal to absolute value of alpha and square of norm of B, and RHS will be this norm of alpha B times norm of B. This is equal to absolute value of alpha norm of B square of norm of B. So, here we can see that LHS is equal to RHS. So, equality holds in Cauchy-Schwarz inequality. So, conversely, suppose equality occurs. Conversely, let equality be there in Cauchy-Schwarz inequality. In the inequality, that is, so this equality occurs only when, while proving this theorem, just recall that the equality holds only when this norm of u minus t inner product of u v times this v, this square is equal to 0. So, this is true if then we get this u minus t times this inner product u v into v is equal to 0, that is u is equal to t inner product of u v times b. So, take alpha as t times u v. So, u and v are linearly dependent. Next, we shall see some consequences of this Cauchy-Schwarz inequality, and one important consequence that we get is triangle inequality. So, that we will write as a corollary, and this is the triangle inequality. It is like this: for any vectors u v in an inner product space V, in an inner product space V, norm of u plus v is less than or equal to norm of u plus norm of v. So, it is like that in geometry we have seen that triangle inequality, that sum of length of two sides is greater than or equal to the length of the third side. That means, if we take the vectors u be like this is u, this is v, then here this third side of this triangle will be u plus v. So, this is the geometrical interpretation of triangle inequality, that length of two sides, sum of length of two sides is greater than or equal to the length of the third side. Using Cauchy-Schwarz inequality, we can give a proof of this, that we obtain by expanding this norm of u plus v, this square is equal to inner product of u plus b, and on simplifying or using axioms of an inner product space, we can get that inner product of u with itself u plus inner product of u v plus inner product of v u plus inner product of v with itself, and this can be written as square of norm u plus inner product of u v plus inner product of u v its complex conjugate plus norm v square, and this is same as square of norm of u plus 2 times real part of this u inner product of u and v plus norm square of norm of v, and this is less than or equal to square of norm of u plus 2 times absolute value of inner product of u v. So, this follows from that property of complex numbers again, plus square of norm of v, and from Schwarz inequality, Cauchy-Schwarz inequality, we get that this is equal to square of norm of u plus twice norm of u into norm of v plus square of norm of v. So, this is from Cauchy-Schwarz inequality, Cauchy-Schwarz inequality. So, now this is equal to norm of u plus norm of v whole square. So, hence we get this triangle inequality by taking positive square root. This is less than or equal to norm of u plus norm of v. So, use here this inner product space also satisfies an important property, that is called the parallelogram law. So, this another important property here we get is this parallelogram law. So, it says that for any two vectors in an inner product space, two vectors in an inner product space, any two vectors say u and v in an inner product space v, we have that u plus v its norm whole square plus square of norm of u minus v, this is equal to twice of square of norm u plus square of norm V, and this has also geometrical interpretation that if we have a parallelogram with sides, that this is vector u and vector v, and if we complete this parallelogram, that the diagonal will represent the vector u plus v, and the other diagonal that represent this represent u minus v. The vector it represents u minus v. So, this parallelogram law says that the sum of squares of two diagonals is equal to sum of the square of sides, all four sides. That means, the sum of square of length of two diagonals is equal to the sum of square of length of all four sides. This is called the parallelogram law. So, this parallelogram law can also be proved easily, that we can find the square of norm of u plus b be like this: u plus v, inner product of u plus b v with itself, and on expanding we get that norm of u square plus this inner product of u v plus this inner product of u, this v u plus square of norm of v, and similarly the square of norm of u minus v is equal to inner product of u minus v with itself, and that is equal to norm of u, the square, minus inner product of u v minus inner product of v u plus square of norm v, and we get the result by adding these two. We get the result by adding these two. So, this Cauchy-Schwarz inequality has many applications. So, let us see few of them. So, application of Cauchy-Schwarz inequality. Here we consider, first we consider that inner product we have defined on C n. In the second example, consider the inner product, on C n, that is inner product of x y is equal to summation x I y I bar I from 1 to n. Applying Cauchy-Schwarz inequality, CS inequality to this inner product, we get the following result, that for any complex numbers, A1, A2, An and B1, B2, Bn, for any complex numbers A1, A2, An and B1, B2, Bn, we have that absolute value of A1 into B1 bar plus A2 into B2 bar plus An into Bn bar is less than or equal to absolute value of A1 square plus absolute value of An square whole to the power half into absolute value of B1 square plus absolute value of Bn square whole to the power half. Similarly, if we apply Cauchy-Schwarz inequality, similarly applying Cauchy-Schwarz inequality to the third example, to the inner product, in the third example to the inner product in third example that is to the inner product space V of all complex valued continuous functions on A B, we get the following result. We get the following result, that is, for any two complex valued continuous functions A B, for any complex valued continuous functions, for any two complex valued continuous functions on A B, for any two complex valued continuous functions f and g say on A B, this absolute value of integration f t g t bar dt from A to B is less than or equal to integral a to b f t mod square dt whole to the power half into integral a to b absolute value of g t its square dt whole to the power half. So, this is how applying Cauchy-Schwarz inequality we can prove many things, and that is all for this lecture. We stop here. Thank you.